Hi class, welcome to the Atomic Structure Review. Recall that all review sheets, in bold, have the major understandings or big ideas for the unit. And below, we'll have some practice problems. So let's get started by looking at a little bit of history of the atomic structure. So we begin with Dalton's atomic model. He's the first scientific relevant atomic model. And his atomic model is called the hard sphere model. So the hard sphere model expands on the idea that all matter is made up of atoms. And Dalton goes on to conclude that all atoms are indivisible. They are hard billiard ball-like structures. Atoms of the same element have the same mass and properties. Atoms combined in fixed proportions to make compounds. For instance, if we have a compound like water, the chemical formula is H2O. So water is always combining 2 hydrogens for every 1 oxygen. And if we had a different proportion of hydrogen to oxygen, like 1 hydrogen for every oxygen, like we have in hydrogen peroxide, we'll have a different compound. And then lastly, atoms cannot be created or destroyed, but they're simply rearranged when they form a chemical compound. So for instance, hydrogen and oxygen form water. You don't create or destroy matter. You begin with hydrogen and oxygen, and then you end up with a compound of hydrogen and oxygen. Now, the next relevant scientist was Thomson. And what Thomson basically did, his model is called the plum pudding model. So what Thomson did is he used an instrument called a cathode ray tube. And inside of his cathode ray tube, he passes an electric current essentially through a vacuum. And he notices that the electric current travels in a straight path. But then what J.J. Thomson goes on to do is he adds an electric field. So when he adds these charged fields, he adds a positive field and a negative, he notices that his beam that originally was going straight through the cathode ray tube is always going towards the positive. So since his beam is always traveling towards the positive, his beam must have opposite charged or negative charged particles. So in J.J. Thomson's model, as we look here, we can see that he finds these negative particles, these first subatomic particles, that are embedded into this diffuse positive mass. Next up, we have the Rutherford atom. Rutherford uses the famous gold foil experiment. In this experiment, he has a piece of gold foil that he goes and shoots alpha particles towards. Now, it's really important that we recall that alpha particles, which are the same thing as helium nuclei, are very massive. So an alpha particle has a mass of 4 and a charge of positive 2. So he shoots these very heavy, positively charged particles at pieces of gold foil. And what he notices is most of these particles go straight through the foil. They're going straight through the atoms. Some of the particles deflect at slight angles. So they approach the atoms and then they veer off slightly. And then a few of the particles, for whatever reason, they basically come in and they are deflected at very sharp angles. So he makes a few conclusions. Rutherford concludes that because most of the particles went straight through, then most of the atoms must be composed of empty space. But since some of these positively charged particles veer slightly they must be encountering a small positive region in the atom. And because even fewer particles are deflected at these very sharp angles, these particles must be encountering a very dense area of the atom. So Rutherford goes on to say that the atom is mostly empty space, and it contains a small, dense, positively charged nucleus. The next scientist that we look at is the Bohr model of the atom. In the Bohr model, he uses a flame test, much like we did in lab. He adds energy to atoms and notices that every atom glows a characteristic color in a flame. He further goes and separates this characteristic color using a prism or diffraction gradient, and notice that the one characteristic color can be divided into discrete wavelengths of light. Now, he notices that these wavelengths of light are constant no matter how much energy he adds or how much time he adds energy for. So he concludes that the electrons in the atom must have discrete or quantized energy, fixed energy levels. So he comes up and he finds what we call principal energy levels, or rings where the electrons sit. He says that each principal energy level has a discrete amount of energy. Bohr goes on to quantify this energy mathematically, saying the electrons on inner principal energy levels, or inner rings, have lower energy than electrons on outer rings. Bohr goes on to establish that there is a maximum set of electrons that can be accommodated on each principal energy level or ring. The first principal energy level can accommodate a maximum of 2 electrons. The second principal energy can accommodate a maximum of 8, then 18 and 32. Finally, we get to the current model of the atom. In the current model of the atom, we have a nucleus that is surrounded by quantized electrons, but they no longer travel in a fixed path or orbit. So in Bohr's model, we could exactly find the electrons traveling in one of these rings. In the quantized or modern model of the atom, we have different shapes for the electron areas, and instead of having fixed paths, they basically are clouds of electrons. We know a region in which the electron is found, but we don't actually know where the electron is or where it is going. So the region or the electron cloud is called an orbital, AL. So remember that in Bohr, the electrons orbit, or they're found on a path, but here in the modern model of the atom, the electrons are located, or likely located, in an orbital. So, reviewing the atomic structure, we are given some questions that are all referring essentially to Rutherford's gold foil experiment. And in the first question, it asks, in Rutherford's gold foil experiment, some alpha particles were deflected from their original paths, but most of them passed through the gold foil with no deflection. Which statement about gold atoms is supported by these experimental observations? So basically, we know that Rutherford said that the atom is mostly empty space and that it has a small, dense, positive nucleus. So choice 1 is the best answer. In choice 2, we're given a very similar question, but in choice 2, instead of focusing on the entire experiment, it asks us to focus on the fact that particles usually pass undeflected through the atom, and that is because the atom is largely empty space. Now, in question number 3, we see, again, a summary first given of the gold foil experiment, and then we were asked to make some conclusions. So in part A, it asks us to conclude about the structure based on the fact that most of the alpha particles passed directly through. So here, directly through is the important part. So we know that the atom is mostly empty space. And on part B, it asks what few of the alpha particles are deflected. So we're here focusing on the deflected. Now remember that alpha particles are positive. So basically what this determines is that there's a positive nucleus. Moving on, the next question asks us to characterize a neutron. So above in the bold, they characterize the major subatomic particles, the proton, neutron, and electron. Recall that the proton has a positive charge, a mass of 1, and is located in the nucleus. A neutron has a neutral charge, a mass of 1, and is located in the nucleus, while a electron has a negative charge, a negligible mass, and is located outside of the nucleus. So here we're asked again for the neutron. So the neutron has a neutral charge and it has a mass of 1. So here we can recall some important components of our periodic table. We'll look simply at the key. So recall that the atomic mass, now here this is an average of the number of protons and neutrons. When talking about a specific atom, they often give us the exact number of protons and neutrons, called the mass number. We are also given the atomic number, which is equal to the number of protons, and we're given the electron configuration. Now recall that in the electron configuration, that is a dash and not a minus sign. So the sum of the electron configuration are the total number of electrons in an atom. Finally, we have a point here. Now here are the selected oxidation states. Now the selected oxidation states are the charge of an ion. Most atoms that we're going to be looking at are not ions, meaning they don't have a charge. And the reason they don't have a charge is because their positive charges, their protons, are equal to their negative charges, their electrons. But in an ion, that is not the case. In an ion, we have a charge because they have gained or lost electrons. So charge is equal to the protons minus the electrons. But in an atom, we can never change protons. That would become a nuclear reaction, and we'll visit that much later. So here we'll never change protons, so the only thing we can do is change electrons. Since electrons are negative, adding electrons results in a negative ion, and subtracting electrons or removing electrons results in a positive ion. So here, to find the number of neutrons, we're simply going to subtract the atomic number from the mass number. Now, again, electrons we talked about are outside of the atom, outside of the nucleus, I apologize, and they have a negative charge. So they are not positively charged. So we'll remove choice 1 and 2. They're negative subatomic particles, and they are not inside the nucleus. They are outside of the nucleus. So choice 4 is the best answer. Now, next we're given krypton 85. So the first thing we need to do is we need to locate krypton on our periodic table. You can do this by first looking at reference table S to find what the element number for krypton is. Krypton is element number 36. So again, here we can see that krypton is element number 36. So here we're asked about krypton 85. So the 85 is similar to this 83 number, but this is the exact number of protons and neutrons, 85. And we can see from our reference table, we have exactly 36 protons. So remember that this is the protons and neutrons. So we must have 36 protons, so we can remove the first two choices. Now to find the number of neutrons, we're simply going to subtract 85 from 36. So that means that that is going to be 49 neutrons. So choice 4 is going to be the best answer. Notice that we also have 36 electrons, because whenever we have a neutral atom, protons, positive charges, must equal electrons, negative charges. In lithium 7, they give us the similar structure, but here they're only asked for the neutrons. So we're simply going to go and subtract 3 from 7 to get 4. The next question asks about potassium 42. So we must look up potassium on our reference table. So here, looking at potassium, we can see this bold number. The atomic number is the number of protons. So potassium has 19 protons. In this case, the mass number given as 42 is irrelevant. A neutral atom contains 12 neutrons and 11 electrons. So the number of protons would be, so here the key word is neutral. And we know that a neutral means no charge, so the positives must equal the negatives. We're looking for the protons. Protons have a positive charge, and we are already given neutrons which have no charge, so the neutrons here are unimportant. And we have 11 negatives. So if we have 11 negative electrons, we must have 11 positive protons. The next question asks us to look at oxygen 17. So again, it's essential that we find oxygen on our reference table. Now, oxygen 17 means that this number, instead of being approximately 16, is actually 17. Now, we're asked to look at the nucleus. So we know that we have the number of protons is 8, and 17 is going to be our number of protons and neutrons. And those are what are located inside of the nucleus, the protons and neutrons. So here I have 8 protons, and I have 17 minus 8, or 9 neutrons. Now, they ask us, what is the charge of the nucleus? Well, we know the charge that is due to neutrons is 0. And we know that the charge that is due to a proton is a positive 1. So when we sum together these charges, we're going to have a charge of positive 8. Nuclear charge is always positive and always the same as the atomic number. Finishing up the last few questions, question number 12 asks about the modern model of the atom. So the subatomic particles located in the nucleus we recall are protons and neutrons. And so the net charge of the nucleus is due to these subatomic particles. Recall that protons are positive and neutrons are neutral. So the charge of the nucleus is going to always be positive. Now, the modern model of the atom shows that electrons are found in clouds. So they are not orbiting in fixed paths. That's Bohr's model of the atom. They're instead found in orbitals or clouds. So cloud is just another name for orbital.